Okay, so hi everyone and welcome to the ICTS String Seminar. Today we are very happy to have Miranda Cheng telling us about machine learning and theoretical physics, some interactions. So please, Miranda, take it away.
Yeah, thanks, Victor. Nice to see you again. And thank you for the kind invitation. And yeah, today I'm talking about machine learning and theoretical physics. It's a little bit awkward, I mean, to talk about it in a string theory seminar because I cannot detect any string theory in it. But the organizers assure me that it's okay. So I hope you guys are not gonna be terribly bored. Okay, so yeah, some advertisement slide. Well, what does machine learning have to do with physics? I mean, obviously, in one direction, machine learning can provide computational aid to physics questions, and machine learning techniques have been, widely used already in subfields of physics, including astrophysics and detector physics, where data pose a very strong, a very big challenge, but also good, most important resources. And there are also more like more speculative or more ambitious ideas about how to use machine learning to help physics. For instance, how to employ machine learning to discover new laws of physics, for instance. And I'm not going to touch on that topic at all today, but just so that you know that we all aware that there are many possible ways to employ machine learning in physics. And what can machine learning learn or obtain from physics? Well, one fact that probably has not escaped your attention is that many physicists switch to machine learning and they make great contributions there. But apart from that, what's the reason for that? I think there's non-trivial similarities in the underlying principles and in the ideas. So in particular, the hope is that physics can provide insights in the interpretability of machine learning algorithms so that it's less of a black box, and maybe to inspire new and different improved architecture designs. Okay, so that's sort of the big picture. And what I'm gonna talk about today is basically what I've done is I put two talks together. So based on my three sort of papers recently in this area, and we will see how that goes in terms of time. But the point is that if you have any questions, please feel free to interrupt. I don't need to talk about every single paper, definitely. So I think to allow time for questions is more important than going over everything. Okay, so the first part is based on this recent paper by myself and with three researchers in Qualcomm in the company. Okay, so what's the idea? And then the idea, the motivation is the following problem, that in order to disentangle new physics from available data, from new data, like including from detectors or from dark matter experiments, we need high precision predictions from within the standard model. Okay, and but for that, we don't have enough computational power. Well, one example, maybe you still remember, is this muon dispute that, if you look at the details, like experts couldn't agree on each other, partially because the lattice QCD computations don't match. Okay. So the question is, can machine learning help by increasing the efficiency of, standard model computations, actually? So for many of you, certainly for myself, this is a change of mind frame. We're not, looking for new ideas. We're not looking for brand new, theoretical insights. What we're doing is we want to improve the tools we have in order to compute better using old physics. Okay, and apart from that, well, there are many places where we need sampling in everyday life. But anyways, let's stick to lattice field theory for now. Well, it is the main computational tool for doing non-perturbative computations in quantum field theory, such as LQCD. And the idea is that we replace, we discretize the space-time, right? And then the goal is to compute observables like this, right? And by replacing the path integral with a sampling computation. So so traditionally using multicolo Markov chain multicolo methods. Right, so the challenge here is the so-called critical slowing down problem of the MCNC. What it is a catastrophic inefficiency, which makes it very, very, very difficult in terms of computational power or available time to sample through enough independent configurations, okay, in order to have an accurate estimate of your observable. And this poses a problem in the limits of continuous limit, usually in the HEP context. Okay, namely you keep the physical size the same, but you chop it finer and finer, then your degrees of freedom, grows. Or more in the condensed matter context when you approach the phase transition point. Okay, so what's the idea we want to use in order to improve on this? Well, what we want to use is a flow-based approach. What does it mean? It means that we have this configuration space, okay, the space of possible configurations. Well, in QFT, of course, that's infinite dimensional. And in lattice, for instance, in the example of a single scalar field, it has this space, right? Well, L is, L is to the power D, that's simply the number of lattice points in your lattice, and D is your space-time dimension. We're doing everything Euclidean. Okay, and on top of that space, we introduce an auxiliary space. We call it the latent space. And then here we work on the special case where the latent space is basically the same as configuration space. So we're looking for an endomorphism. Okay, such that on the latent space, we sample with a distribution that's just given, call it the rho of Z. And then this rho of Z gets pushed forward and becomes a distribution on the configuration space, which is what we need in order to sample. Okay, and then this is related to the original latent space density with a factor that's given by the determinant of the Jacobi of the flow, okay? So when is this approach gonna help us? Well, there are three elements that I regard as the key to computational feasibility and efficiency. The first one is the latent space distribution, which is the thing you're actually going to sample, has to be easy to sample. For instance, we just take independent Gaussians. So you have a free theory if you want. Okay, and the second thing is that in order to compute the push forward probability, the determinant of the Jacobian has to be computable, okay? You can't use some dirty estimator that screws up your accuracy. And the third thing is, of course, that this push for probability has to be a good approximation of your so-called target physical distribution, which is just given by the action. Okay, so that's the key. And these three things are things we want to achieve. And let's start with the last point, namely how to make sure that the push forward probability approximates well the target's distribution.
Can I ask
well, yeah.
So, I mean, it's not clear to me, like when you say, for instance, in the context of, let's say, a scalar field.
Can you speak a bit louder or closer to the microphone?
Yeah, yeah. Can you hear me now?
Yeah, a bit better, yeah.
So in the context of, let's say, a scalar field, what would be the variable z, like in the previous slide, that in the last slide you had? You have z and you have a function of z, right?
Yeah.
Or z, so, right?
Yeah. So you mean here? Yeah. Here.
Yeah. So what is z and what is like? Can you just explain this? What's going on?
Okay. So this is a point. This is going to be phi corresponds to labels a point in the configuration space. And the example of one scalar, single scalar field, it just gives you like the value of the real scalar field at each lattice point.
Mm-hmm.
Okay, and z is a point in the same space. Okay, it's in the language of statistics. It's a random variable in the language of when we're talking about probability.
I see. So okay, so you're going from the configuration space to itself. Like that's why.
In this case, in this work, we consider the cases where the latent space is the same as the configuration space. While in some other work, you can have like a smaller or a larger latent space than the actual configuration space. But in this work, it's you go back to itself. It's an endomorphism.
So the flow is a sequence of endomorphisms on this space, on the configuration space.
Yeah, it's a sequence or just one, depending on your architecture. But I mean, in the end, it's just an endomorphism to it. Yeah. Okay. On the configuration space. Okay. And we don't know what it is yet.
Thanks.
And the name of the game is to find the right F that does the job. Thank you. Are there more questions? Okay. So coming back to the question, how do we make sure that we get a push forward probability that approximates the target probability well? The first step is to choose an ansatz of the flow. Okay. And then because of the second point we just said, we want the flow, the ansatz to come with a computable Jacobian, or at least the determinant of the Jacobian. And then we parameterize the possible flows with some parameters. Okay, all this is gonna be concrete soon, but now it's just the idea. Okay, for instance, if it's a one-dimensional space, you can say like F equals what? Theta times Z, right? Then you're just, the only thing parameter you can tune is the slope. And that's one example. Okay, and then the next example, the next step would be to find the parameters that minimize the so-called reverse KL cost function. And what is the KL? What is the reverse KL cost function? Well, this KL divergence is a measure of how different two probability distributions are from each other. So how large the difference is between the two probability distributions. So its definition is given like this. So QF it's important that it's reverse KL. Let me go to that in a second. But it's a QF times the log of the ratio between QF and P at 0.5. And then we have to integrate over 5. Okay. So that's a L to the D dimensional integral. Right, so to approximate this, right, we again use sampling. And then because what's multiplying the log is the push forward probability, not the target probability. So we can just sample using this according to this Gaussian distribution that's easy to sample in the lattice space. Okay, and then we write it in this way. Here we use the specific form of the target distribution that's given as a Boltzmann weight. And then we throw away the constant involving the partition function, Z, since it's theta dependent, so it doesn't play any role in the optimization. Okay, and the key point is that this training, using this loss function to train the F is different from what we usually think about when we think about machine learning. Namely, you need a lot of training data and so on. It's sort of self-trained or bootstrap training if you want, because you're sampling using, not using, any data. You're just sampling using your own distribution. Okay, and measure how bad it is, and then you change from there. Okay, so that's a very important thing, because we don't want to set up the problem that we can find F only if we already have a lot of MCMC data. That would be self-defeating, right? Then we don't need machine learning. Okay, so that's the training part. So to recap, what we need to do is that given an ansatz that parameterize your F, what you need to do is you draw samples, well, according to your Gaussian in your lattice space, and then you compute the previous slide, the KL loss function or cost function, the same thing. And it's a function of theta. And then you do gradient descent. Well, in practice, stochastic gradient descent, but that's technical aspect, and towards the minimal of KL, and then you update theta in this way. And if it's not good enough, KL is still big, and then you do it again, and do it again, and do it again, until, well, you think, okay, the KL divergence is small enough, it looks really like the target distribution. So we save the model. Save the model meaning you just save the parameters of your model. And then you start to build Markov chain using the push forward distribution. Okay, is that clear?
Sorry, I have a question. We don't know the target distribution in these cases, right? Because you don't, so how do you compute the loss function actually? Or?
Yeah, so here we don't know the partition function. That's too expensive to compute. Right. But given any configuration, since we have the F, so we have the image of F, which is the candidate phi, right? Yes. Yes. We can compute the action. It's not difficult to compute the action. You just plug in your values of phi.
I see. So sorry. So F was the thing that was doing the push forward from this latent space to the physical space.
That's right.
Right, but I thought we are trying to find a good value of. Aren't we trying to find a good map F?
Yeah, a good map F here means good map F within your chosen ansatz. So you want to find a good theta.
I see. Okay, fine. So you want theta within your ansatz. So theta is some parameterization that gives you the ansatz.
Yeah.
Very good. But now, sorry, I still haven't understood. So if you just know F, how do you know that's doing anything like the real partition function, which, as you said, is too expensive? I mean, I'm missing something simple. Maybe could you just explain?
Yeah. No, that's a very good question. Like choosing the F of theta, that's the art, right? You want to choose F of theta, which is an ansatz,
Yes.
I don't know if it's visible, but anyways, I'm not writing anything important. So such that, you know, it's flexible, it can approximate all kinds of distributions, at least your type of distributions. You want it to be flexible enough, okay? And then here you might want to quote some blah blah from the lore of machine learning, that the deep neural network is a, you know, is like a universal approximator of any function or whatever. But you also don't want it to be like to be too high dimensional, to have too many thetas, that your stochastic gradient descent is very ineffective. It gets stuck. It's not working. It cannot find a minimum. So it's a balancing act to find the right ansatz. But so far, I'm just, you know, talking about everything like given an ansatz, what you do.
No, I understood that. I guess maybe the first equation to the second equation. Oh, are you saying because this QF is some probability distribution, so that just gives you a constant? Is that the statement? Sorry, I'm trying to understand how you went from the first equation on this slide, the first line, to the second line.
Yeah.
As you said, the first line depends crucially on how close Q of F is to P. But we don't know what. So, how do you get rid of P in the second equation?
Yeah, so P is this red equation, right? It's our target.
Yes, and we don't know that, right? But we still want to compute the loss for a given Q.
No, P is known because we do know, for instance, the action of QCD.
Oh, I see.
So you just plug it in, and Z is hard to compute, but fortunately, Z terms just drop out.
I see. Okay, thank you.
Yeah. Thank you for the question. If you see it for the second time or third time or fifth time, it's very confusing.
So, sorry, Miranda, question about the motivation. So why is it that doing this Monte Carlo sampling for the action itself is more difficult than doing it for the Gaussian? This is probably a very basic question, but because that somehow is the motivation for the whole work, right?
Yeah, why Monte Carlo is more difficult than what?
Why doing Monte Carlo sampling for the actual action is expensive compared to doing Monte Carlo for just the Gaussian distribution?
Yeah, so Monte Carlo, well, the problem is what traditional, just plain vanilla Monte Carlo does is that it updates, you know, in the Markov chain, you start with one initial configuration, and then you flip a few spins, let's say, and then you see if, you know, this new configuration that's obtained from the first one by flipping a few spins is rejected or accepted. If it's accepted, then you keep it, and then you keep doing this. Okay. But the point is that most Monte Carlo, it's a local you know, updates. So then you could imagine that when your lattices gets very, very large and has a non-trivial landscape, then it might take forever for it to sample through the configuration space in order to get a good and trustworthy estimate of your observable. That's the problem of the Monte Carlo. And of course, within the Monte Carlo community, there's also innovations from this. There's Hamiltonian Monte Carlo, and you can, you know, impose some non-local updates and so on, but it's still, you know, difficult to surmount this this problem of critical slowing down. And here at this, you know, on the other hand, we don't do any local updates, right? We just directly sample from the latent space and then push it forward into your configuration space. So it's, in some sense, it's independent sampling. You don't, I mean, you sample each time fresh.
Okay, so, but locality is useful in quantum field theory, right? I mean, you know, the local configurations will not be too different from each other. So locality is useful in that sense rather than doing things completely non-locally.
Yeah. And then as you will see later, we also make use of the locality property. Or if you want, you can let the network learn the necessary locality property. But I mean, for instance, if you have like a long range correlation, like when you approach the phase space, then this becomes really prohibitive. to do just local flips. Right? It takes forever.
Just to understand, if in the special case of free theory, you think this would be useful, or just using the action would be useful?
Yeah, just using the action is already the same as sampling the lattice space.
Because it's Gaussian.
Yeah, because it's Gaussian.
And
yeah,
even in the perturbative theory, this would be true?
Yeah, so this is especially, I mean, when do we resort to the tools of lattice quantum field theory? Is when the theory is strongly coupled, is non-perturbative. We can
this is just to understand the motivation. Yes, thank you.
Yeah, of course, that's important. Thank you. Are there more questions? Okay. So here at the end of this slide, and then in the next slide, I'm going to explain the last step before we give details on the first steps. So how to build Markov chains once you have a trained network.
Sorry, Miranda, sorry to interrupt you again. I just wanted to clarify a couple of things. The critical slowing down in Monte Carlo, it happens because as you get closer to your target probability distribution, the number of samples which get rejected becomes a much larger fraction, right? That fraction keeps increasing. So eventually, you know, almost all your choices are being rejected. And secondly, on the question about locality, I mean, we don't necessarily want only local configurations, right? Because if we did, we would never explore, let's say, different topological phases of the system.
Yeah, that's right. Yeah.
Right. Yeah. So Monte Carlo would be insensitive to such states.
Yeah. So I mean, again, there's been also great innovation in Monte Carlo methods that try to, you know, update non-locally, and, you know, just putting by hands non-local updates. But and then the first point, I completely agree. In fact, later I'll show you plot when I show you the results of our experiments, like how we evaluate the quality of the network is by computing the acceptance rate, like how often a sample gets rejected and how often when the acceptance rate is low, then indeed that's what happens when you have critical flow slowing down. Yeah. Okay. Is that clear? Can I go? Okay. So I just want to say one thing about methodology. Now, once you have a good enough map F, then what you do to how you use this model is to use latent space sampling, as we said, plus a metropolis Hastings step in building your Markov chain. And what that means is that, well, because we know we have the confidence that our push forward probability approximates well the target distribution, but we are also certain that they are not identical, and we want to account for that, you know, error. And one way to account it is by adding this metropolis Hastings step.牽we use the pushed forward probability to propose a sample phi t plus 1, the next step, the next sample, the next configuration. And then we reject it or rather accept it with this probability that's given by the mean of between 1 and the ratio of the true probability distribution ratio and the push forward probability distribution ratio. And as you could see again, if you know our approximation for the distribution is exact, namely P equals Q, then we will always accept this sample. So that's the intuition we want, of like why this step can help us to correct our sample. or to improve on the sample qualities. And theoretically, we know that with this step and the asymptotic convergence of our sample to the target distribution is guaranteed. But that's theoretically speaking. I mean, this work is anything but theoretical. Okay, so this is the Metropolis tasting again. All right, so so this idea of using the flow is not starting from our work, and actually in 2019 there has been a paper by the MIT group and later the DeepMind group and the NYU group, the same group together, the same team, on flow-based generative models for Markov chain, Monte Carlo, and lattice field theory. And their testing case is the 5⁴ theory in 2 dimensions. Okay, and actually we started around the same time, but we are just much slower in obtaining results if you want. So what they do is, well, I won't go into details of their model, but the idea of using the flow model, everything that I have talked about so far till now also applies to their paper. So, as we know, and as this paper, very nice paper, pointed out this year, that their proof of concept study is great, but we also know that it's not really usable, because what the situation you face is that you have a critical slowing down of training instead of a sampling. So the cost of training the network, their network, till an acceptable acceptance rate, sorry, I haven't defined it already. I haven't defined it yet, but thanks for the question. The acceptance rate is how often your proposed sample gets accepted. So if it's really, the acceptance rate is really low, then you have a problem of critical slowing down at the phase of sampling, and it's that means your network is unusable. So here the problem is that if you want to train your network till that's an acceptable acceptance rate is attained, then the cost of it scales very deeply with the lattice size. And in fact, they can't run for 2-dimensional lattice of size more than 20. 20 is already very, very tough. Great as a proof of concept study, but it's still not great as a beginning point of any real application. You can see this plot is a log plot, so the cost grows exponentially. Okay. So so we've been scratching our head, or actually coding for 1.5 years, trying to find something that works better. And the first thing we wanted to pay attention to is symmetries. So the problem, let's take the same toy model, okay, 5⁴ in 2D. Okay, the space-time, there's space-time symmetry. Well, that's just the space-time symmetry of 2-dimensional periodic square lattices. There's rotational reflection and shift symmetry and all that, and nothing else. And the global symmetry is also very simple, it's just a Z2. But what we want is we want to bake them in instead of hoping that the network will learn them. It's always a little bit of a tension in designing machine learning architecture, whether you want everything to be learned or whether you want to put in as much prior knowledge about the system as you want. And our attitude is that symmetry is such a fundamental thing that we should incorporate symmetries in the architecture design as much as possible. And I don't have time to show you the plots, but that's supported by various experiments. And the second thing we want to do differently is we want to use a continuous flow, what's called the neuroordinary differential equation. So what is it? Well, it's a differential equation. It's an ordinary differential equation. And what you want to do is, what you want to learn is actually the gradient, okay, if you want, or the vector, as we call it. Okay, so then how do we build this flow? Well, we'll build this flow by using an ODE. We take, the drawn sample if you want, the latent space variable as the initial, the initial condition, and then flow it for a given time big T, and then we call it our phi, and T is fixed in this equation. And then at the same time, you run another ODE, which is the ODE of the probability distribution, of the push forward probability. So this F is really now an F of T, right? So you can terminate at each point F in principle, and then you get another map. So then you also run this ODE, like basically it just comes from the Jacobian factor again. So that once you're done with computing your flow, you're also done computing the push forward probability distribution and everything. Okay, so so that's the idea. So what's the advantages? So this neural ODE scheme was proposed in this paper, NeurIPS 2018. And some of the advantages include, like, we have very flexible choices of the vector field. And for generic choices, I mean, the flow is immediately invertible. And then it requires modest memory cost, but I'm not going into this. So a computer science seminar. And then what especially is attractive for us is the potential to be interpretable, right? So you're basically flowing in some sense from field theory to an interacting theory through a continuous flow. So yeah, well, that immediately reminds one of the RG flow, but that's something that we're still working on. Okay, so now, finally, the meat is how we parameterize the ansatz of our vector G. So, okay, so we have lattice points X, and then we want the gradient to be non-local, to be non-free, actually, to encode interaction. We want it to depend on the configuration at point Y. Okay, and then we do this as like a Fourier analysis of phi. And then this is a constant, a real number given X, Y, A, and F. F is the frequency, which is learnable, and X, Y are the points on the lattices. And what's K of T is like different time shift kernels. So, so different A corresponds, for instance, this yellow A is just turned on early and then turned off later. So what it enables you to do is, if you wanted to think about it as some, dynamics of a particle, then it allows you to exert some forces, right? Time dependent at certain points during the flow. So that the time shift kernels, these are standard. And so our theta are these, the frequencies, and these coefficients W. So that will allow, a certain number of frequencies to be learned. So the dimension of the space is a hyperparameter, meaning they're not parameter, they're given as part of the architecture, not learnable. Okay, any question?
Why is this kind of flow equation, why are you using this particular kind of flow equation for this shallowness?
So you are, well, what I have explained is the motivation, some of the motivations to use a continuous flow instead of, layers of discrete transformation. And then some part and about the specific form of the ansatz. Well, I can tell you we've tried many things, but this is actually in the end, the simplest, the most minimal of what we have tried, and it works the best. Okay. And then an important part of the motivation is symmetry, which is what I'm going to explain in the next page. Okay, so
doesn't look so simple. I mean, you have d phi x dt on the left hand side, and on the right hand side you have phi of y, sine of omega phi of y. It doesn't look the simplest of equations, right?
I mean, if you look at if you analyze it in terms of the number of parameters your neural network has, then this is really a tiny network. This is simple in that sense. The number of thetas is very small.
Number of thetas.
Theta is like f of theta is abstractly the symbol for the collective of all the parameters in the flow. Yeah, I'm not saying it's easy to integrate or something, but it's not. It turns out to be not hard to integrate using an integrator. But one reason to make it simple is the symmetries. First of all, because we want space-time symmetries to be baked in. So actually, this W only depends on if you want the distances between lattice points. Okay, so your physicists say, duh, of course, yes. And then the global symmetry is just encoded in the fact that we only have sine, we don't have cosine from a Fourier point of view. So that if you have prior distribution, if you have a lattice-based distribution that's invariant under Z2, which we do have like the Gaussian, then under this flow, it's guaranteed that the push forward flow distribution will be invariant under phi and minus phi. So which is, well, actually a simple thing like that can, can have consequences. For instance, if you go to the broken phase of phi to the fourth, right? If you force a machine learning algorithm to learn the distribution, then what often happens is that it only learns one mode, okay, because of the nature of the cost function or whatever. But I mean, using this flow, that would never happen, that it only learns like one vacuum. Okay, and then you can also see from data that actually space-time symmetries are also better to be baked in to be manifest. Like this is the results using the algorithm of the other team. I mean, you could see that they only have approximate invariance that actually can go pretty off. And the even more surprising thing is probably that the symmetry aspect doesn't improve with training, sort of like network somehow just doesn't learn the symmetries, but okay, it has its reasons. But so using that simple flow, the experiment result is a drastic improvement of scalability. So for instance, well, by the way, in their paper, they already compared their results with the traditional MCMC result and then got the conclusion that their flow model works better. So we don't need to compare with the MCMC anymore. We just compare with theirs as a benchmark in the machine learning era. So you could see like dashed line is our model and solid line is the previously proposed flow model. So for L equals 6 or 6 by 6, really tiny. So the difference between dashed line in performance with dashed line and solid line is probably not that huge. But if you look at L equals 32, then no matter how many days you train, their network doesn't train it into anything close to being usable. But our network is, I mean, above 60% acceptance rate is very usable as a sampler. So, okay, that's the content of the paper and what to do. To to keep pushing on the physics front, well, the Go application is again lattice QCD. And then clearly to really be usable, scalability is a crucial must. And then once, you know, now we have like a scalar field working, and the next point would be to incorporate gauge symmetries. And then the next step would be to incorporate fermions. And then hopefully one day we can hand it to a phenomenologist and then really turn it into something useful. And then the second, well, front, the pushing on the AI front, but the complexity and why are people in AI also interested in physics problems? Well, the complexity of the lattice field theories and the prior knowledge we already have as physicists or as humans on these theories make them into like ideal testing grounds for new sampling techniques. And also on physical systems, we can hope for more interpretability that hopefully is, you know, migratable to other scenarios, AI scenarios, the interpretability problem. And then I think, yeah, that's the end of the part one. So before I start to, you know, give more talks, I mean, perhaps I should again pause for questions.
Sorry, is this was this still only 1 + 1 dimensions 5 to the 4th theory, or was it also a higher?
Yeah, it's 1 + 1.
I see. So can you, but so you explained the scalability thing, but can one actually obtain some non-trivial results? I mean, are there some non-trivial results one can get by running the model, which one couldn't have got other? I mean,
yeah, that's on the list. I think we tried to run 3D model once. But I mean, we haven't done any sort of optimization or, you know, things like that. So, but that's really on the list.
I mean, I guess it's soluble, but there might be still some questions that might be hard to answer by other techniques. And can one ask some questions which, you know, even in the 1 + 1, I mean, leaving aside 3 + 1, is there some new physics that we are able to learn?
New physics. Well, people are doing new physics from this.
Yes.
From the flow model. Well, there are people like, for instance, like using AI to compute RG flows and that kind of things. And I don't know. And then there's also a paper again by the MIT DeepMind group to like see how well they can sample in like the broken phase. And so, but I mean, that's still not really physics. And I mean, that's not anything we do not know.
I don't know. I mean, you can do 1 + 1 dimensional scalars. You could even do like JT gravity or something, no? Or not really? You might even be.
Why not? Why not? I haven't thought about it, but I mean, why not? I mean, if there's, you know, if there's questions you have in mind, then maybe.
I see. Okay. Okay.
Yeah, but as you say, as you could see, this paper is really basically a completely engineering paper. Yeah, but it's good to talk to physicists and see what they want to do with it.
And to be sure, the flow is in some vector space, right? I mean, it's not. Is the flow in some vector space?
Yeah, here the flow is just in the space of like
in this
R to the L square. This, right, in this space.
Yeah, correct. So that is some vector space.
Yeah. So what we're doing right now is to design flows before applying it to models. We want to design flows on spaces with non-trivial topology if you want. Well, the reason is, well, if you want to, for instance, you want gauge fields, right?
And f is like a vector in that vector space, right?
No, f is an endomorphism and G is a vector. This gradient G is a vector.
F is the endomorphism, okay.
Yeah, yeah. G is a vector.
And what is that equation finally, that sign equation? The G is of the form of that sign equation, right?
Yeah, the whole right-hand side is G.
Right.
And then you can see we allow for explicit time dependence.
But the form of G should be determined by the specifics of the model that you're trying to model, right? I mean, it shouldn't be arbitrary. I mean,
yeah, the point is that you can use any ansatz for G. That's one of the attractive features of neural ODE. Like here, this is our choice. And well, coming up with the right ansatz is to a large extent the art of things.
Sorry, Miranda. I had a question also. Can you say a few words about what is exactly the algorithm you use? So is it a neural network? And what kind of neural network?
Yeah, so this is if you want, this is learning. This is the network, right? So this is the ansatz, and so in sort of parlance, this is a very shallow one-layer network.
Okay.
And one layer, and it's not deep and it's not wide, because I mean sometimes you sort of go wider and then shrink again. And but our width is exactly the same, like, you know, that's why which refers to the fact that the configuration space is the same as the target space. Is a config, yeah, the latent space is the same as the configuration space. So it's not like getting wider or anything. So it's just a fixed width, one layer, very shallow network. Although, you know, it's in principle, this is continuous. So you can also think about it as the infinite depth network, depending on how you want to think about it. But usually, if you have one neural ODE like this, then this is like one depth one.
I see. Sorry, so why time shift is needed? Why this kernel of time shift is needed? Huh?
Well, to increase the expressiveness of your flow, right? So as I said, you want the flow, the ansatz to capture like many possible flows. That's, you know, you want to ansatz, you want to, well, you might not want a universal function approximator, but you want something that's to the practical uses approximate that, right? So you want to be able to generate a flow that can approximate your interacting theory and has no resemblance to your free theory a priori. So the time shift kernels, as I said, if you want to see this ODE as some kind of particle motion, it gives you the freedom to push, you know, to push it, to exert force.
So to be sure, I mean, for different, say when you're designing some, I'm talking generally, so when you're designing some neural network for some, say, images of cats, recognizing the images of cats. Okay, so for that, there would be some kind of specific sort of flow. And for what I'm saying is, for different problems, there would be different sorts of flows, right? I mean,
yeah, I mean, if so we have that understanding, that would be really great. I mean, in fact, I mean, I'm not pretending to be able to tell anyone why this flow is better than the other, right? This is experimental, not even experimental science. Hello?
Yeah.
Yeah. So eventually the thing works because it works. So it's a good horse because it runs. And of course, we're in the process of understanding what are the good principles in architecture design and in the network design. So for instance, here, like the most basic principles of like baking your symmetries in already is not always a common practice. It's often not. And while we, at least when we start with, we know that we want this flow to be symmetric. So there's a lot of trial and error involved, which took 18 months, more or less. So I can't tell you exactly, like, if you have a gas model, this is what you need to do. I mean, there are many very nice papers on how to, you know, how to apply this kind of neural networks to different physics problems, to biology problems, and yes, they all end up using different types of architecture, different types of flows, and I think we're slowly still in the very infant stage of understanding, like, very sharply what kind of questions needs what kind of flows, or maybe not flow at all. Maybe you should use reinforcement learning for this problem or whatever. That's all, like, that's what the game is about.
So this differential equation is sort of, you solve for this differential equation in some way, or how does the machine learning part come in inside this differential equation?
So maybe we should leave this discussion for after the talk. I think Miranda also wants to talk about something else, right? And it's almost 4.
Yeah, so I certainly cannot skip the totality of part 2. I need to cut. And in order to know what I cut, and
no, but
it will be great to know how much time I could make use of.
Yeah, so there was a lot of questions and discussions. So just tell me how many time do you think you would need?
Okay, so I will try to wrap it up in 20 minutes.
20 minutes, yeah,
15.
20 minutes is fine. Yeah, this is fine.
Yeah.
No problem.
Yeah. Can I ask a question?
Sorry? Maybe it's better if you could type your question in the chat box.
Yeah, sorry, I had other mics on in this room,
okay.
But okay, it's fine now, I guess. So yeah, I was wondering, like, would this like help us figure out some dualities or something, that kind of thing? Do you think, like, how would that work out?
Sorry?
Would this approach, like just mapping to some configuration space and so on, would it help to like figure out, say, new dualities or something like that, say in these 2D models?
Modularities? Did I?
Dualities, I see.
Dualities. Well, could it discover that 2 theories are dual? Well, I think this is a great question, and then it's certainly worthwhile to take a concrete theory example of a duality, and and then design a network and see if it learns. I bet it's doable if you just have a very simple T duality or something. But I haven't tried.
Maybe something like more understood, like some Bosonization or something.
That's a bit fancier. I wouldn't know. If I were going to answer this question, I would certainly start with duality, T duality. And if I know how it works, then I might try fancier dualities like Bosonization, more, yeah. Yeah, but there's infinitely many questions one can ask. Okay, so part 2 is like an older talk. It's like, well, when a physicist tries to understand conv nets, so I will focus on a very specific and extremely simple conceptually neural network. It's a convolutional neural network. So a typical problem is like it's like a YouTube AI. It's like image recognition. You want to recognize handwritten digits, and the input is 28 by 28 times 1 dimensional, right? And the output is 1 times 1 times 10-dimensional. The 10 is just 10 class scores. I mean, you get, so the output is like scores for 0, scores for 1, scores to 9, and then you pick the one with the highest score. Okay, and to such a image recognition problem, so regular fully connected neural networks do not scale well with the image size. As you could see, fully connected means any neuron is connected to any neuron in the adjacent layers, and that sucks because I mean, when the number grows, then the number of connections also grow quickly. And then the insight of convolutional neural nets is that it uses properties of the images, namely the locality and symmetry, to reduce the number of parameters. And a typical architecture will look like this. There's layers of feature learning, and there's final layer, which gives you the classification, like a car, a truck, a van, or whatever. So with focusing on the feature learning part, it's usually done like a convolution layer and a nonlinearity, and then a coarse graining, namely it's what's called the pooling. So you reduce, quote unquote, the image size at each step. Okay, so convolution, what is that? It's basically an affine transformation, okay? And then, so here are some matrix multiplications, and the filter size 3 by 3, meaning that, you know, the outputs of one pixel only depends on the 3 by 3, you know, square that this output pixel is in. Okay, so we're using locality. It doesn't care about what the faraway pixel is doing. And then we exploit, for instance, the translational symmetry, and that meaning like if you have cat and you shift the picture a little bit, it's still a cat. So it leads to weight sharing, namely the weight, namely the slope in your, you know, affine transformation, if you want, remains the same throughout the picture. And then the second step is nonlinearity, or it's called activation. For instance, this is the ReLU that's often used, or the sigmoid, the softer activation. That means if your signal is below a certain threshold, then it simply gets truncated, not passed on. Okay, so, and the next step would be pooling, or just coarse graining. For instance, this is often used, very rough, max pooling. So pool size 2 by 2, for instance, here in the pink square, you just choose the largest one, and that would be, you know, the value for the next step, and so on and so forth. So it's not very non-trivial, never very non-linear, I meant, and very rough. So, but it works. An example would be like this. Okay, if you have car, so the output label includes like car, truck, airplane, and so on and so forth. And then you just have a few stacks of convolutional. So our affine transformation and ReLU, the activation, and so on and so forth, and then pull, and then you do it again, and then you pull again. So your image size becomes smaller and smaller, which is, yeah. So the pulling, the coarse graining steps really reminds one of, you know, the block decimation renormalization group flow. Okay, so well, one paper I've written on this is like, it's very simple. It's just like, okay, so CNN is very successful, extremely successful, and it's like revolutionized the thing. Like all of a sudden people believe in AI. But I mean, we also wanted to work beyond flat spaces. So for instance, for all kinds of applications, including on spying on people using a spherical camera. And okay, and especially, you know, the signals are not necessarily scalar. So in the weather application, you have like this vectors as signals. And then I'll be really quick, just like how to do convolutional neural nets on non-flat space-time. I mean, I think we all know the answer. We want to use, again, locality and symmetry. But I mean, the question is, how do we define convolution and weight sharing in this case? So let's start with a convolution. So this is a paper in 2019. Okay, so well, before, I don't even need to give you like the detailed equations, because we have all studied GR. So in principle, we all know what to do. We need to do parallel transport. We need to, you know, have the right indices at the right place, and we need to include the volume factor when we have a non-flat space-time. So this is, I need to explain it to computer scientists, but I don't need to explain it to you guys. And then, okay, again, the weight sharing. So how do you transport the kernels? Well, here, the weight sharing should be phrased in the following way, namely when the input signal, which is localized, assumed to be localized, is parallel transported along the curve, and the output signal should also equal to the parallel transport of the previous result. And then we all know the only way to achieve it is to parallel transport your kernel along the same curve appropriately. So, okay.
Miranda?
Mm-hmm.
Is that is that equivariant? That condition, yeah. Is that the condition of equivariance?
Yeah, yeah.
Right.
Yeah,
okay.
That is what we define to be the condition of equivariance in the non-flat space-time, which, by the way, also includes space-time. I mean, if you have like a moving signal and so on. Mm-hmm. Okay, so that's what the paper, the workshop paper is about. I don't need to tell you much details, but I mean, the implementation, of course, it's an interesting problem that I was not involved in. You have to discretize your non-flat manifold, right? And then do the integral properly and so on. So for instance, this interesting work, they implement equivariant flow, CNN like equivariant flows on, I kept saying flows. Sorry, on the icosahedron, which is approximation of the sphere. Okay, so again, next paper really quickly, and it's more like it's a lot of fun. And then the question is then, can we understand convolutional neural nets in terms of quantum many-body systems? Well, I'll explain why this question even makes sense. Well, and then there's a question of whether it's useful at all to think about it in this way. But first, okay, so this paper with my previous student, Vasilis. So first, to explain why to ask this question. Namely, well, we have the curse of dimensionality in image processing, like, you know, obviously, like the number of possible images like grows exponential, right? And then this is exactly the same as quantum many-body system. So, but we also know that the actual data, namely realistic images as opposed to white noise, lie in some tiny subspace of the space of possible images. Okay, so this is very reminiscent of the states, at least the states below a certain energy level in the Hilbert space of the many-body systems. And can we use the tools there? For there, we know that we have great computational advances given by, for instance, tensor networks. I mean, can we try to understand the structure of data here? And this is a very relevant question. For instance, if you look at this picture, right? It's clearly a panda. And if you add epsilon amount of noise, it's still panda to us, but to the supposedly successfully trained neural nets, it reports a given with very high confidence. So what this is doing is that it finds the, you know, it finds the steepest direction in the space of possible images that takes, you know, the energy function, if you want, far away from the ground state function for the panda network, right? So in this is how they could find this very specific type of noise to add to screw up your network. And in order to do that and to prevent that from happening, you need to have a good understanding of the structure of the subspace where the data is living in. And we also want to understand why such a, thing works well. And okay. So what we have done in this paper is that first we built a neural network that could be interpreted as a quantum state. I'll explain what I meant by that. And then we make sure that it does what a neural network should do, namely it classifies images successfully. And then we study its properties as a quantum state. For instance, we compute the entanglement entropy. Okay, and the third point we did not report in the paper. Okay, so we take this structure, we take this architecture, and we start tweaking it. And then we, in particular, we took away some of the features that machine learners thought that was important, but for us, we don't like it because it's not quantum mechanical, but it turns out that it still works. So we remove, in particular, the nonlinear layer, the ReLU, the activation from the convolutional layers. And instead, we just add an initial feature layer, which is nonlinear. And for the rest would be actually completely linear. And then we also do pooling, but our pooling is not max pooling, but we do product pooling. So 2 pixels, we just multiply the value of the signals together. That's crazy, but it's quantum mechanical and it works. Okay, so the architecture on the left with batch normalization convolution, and then can be described as a tensor network as a result. So in some details, I'm not going to go through it, but what we do in the initial layer, which is we map a grayscale image. Well, you can also do color image, but just but this is what we do for the sake of simplicity. We map it to a normalized state. So norm 1 in the Hilbert space. That is a tensor product of the local Hilbert space, just like in quantum many-body system of this dimension. Okay, so where big N is the number of pixels. So in particular, okay, so what is a grayscale image? So it's a bunch of numbers one for each pixel between 0 and 1, right? Encoding how black or how white this pixel is. Okay, so we map it using like some Fourier basis to some quantum states. And this local Hilbert space is just then, the space of L2 functions on the circle with some cutoff of frequency, right? But you can also choose any other orthonormal basis, like Lagrange basis. We also tried and it works. Okay, so you have now an input image is a quantum state in your language, and the output is a number. And then all that goes between is linear. So that's, you can describe the network as a state, okay? And then
Can I ask a question?
Yeah.
So what's the difference between like you do something like this or just train your network with some data which has some noise in it? Like if I just train my data with some images, say in the case of Panda with some grains in it, wouldn't it have been still fine?
Sorry, I don't understand the question.
As in, I thought you were motivating this by saying even if you have a slightest amount of noise in an image, like it seems to be taking it too much away from the.
It's an interesting question.
Isn't it a kind of like a question about like you probably use too high definition training images or something like. Had I trained with sufficient bandwidth of error in the image, say at the level of grains, wouldn't the network have been good to, wouldn't have trained it better? Like,
I still don't quite understand. How should I train it to train it better? Add noise?
Yeah, I mean, if your images had noise, like as in like the images you showed for the pandas, like
yeah,
it just had.
Yeah, but I mean, here the question, you can ask the question in a different setup maybe, but here the question is a classification task question. Then you train with the given data, right? Data that are already labeled, like picture of panda and panda. So you say like, I throw in, so actually we have done that to the experiment just for the fun of it. We generate a lot of random noise, white noise, or just random noise, random pictures from random generators. And then we give it the 11th label, noise. And then see if the network learns it. And sure it does, right? It learns that this belongs to the noise label, but you can't label everything like that, right? Then if you throw in the picture that's a superposition of a panda and the noise, it still doesn't know what to do.
Okay, so you're saying you're genuinely getting something new here, which you wouldn't have been able to train your network to do had you just extended whatever training data you have. Like say you just multiply it with some bandwidth of noise added to it and train your network with that larger training data. You're saying it still doesn't learn to.
Yeah, but because I mean, the right approach is probably to go beyond the supervised learning, right? To move to unsupervised learning where there's no fixed, labels you have to choose from. And then, but that's a different sort of game.
Thanks.
Yeah. Yeah, so anyways, the gist is that we can describe the network as a quantum state, and the parameters of the quantum states, if you want to expand it in orthonormal basis, would be given by the network parameters the network has learned, right? And the classification will be just, whatever label that gets the largest amplitude will be the correct label. Okay, so you could give it a probabilistic interpretation in terms of the network states. So as I said, so there's a joint distribution, and you can indeed check that this is a completely legit distribution, and which is consistent with our classification, like given an image, which is X, what's the probability that it belongs to the label Y, okay? So fine, so anyways, the result is that this network works, okay? And it works just like on par with whatever the usual benchmark architecture is. So it works just as well as the conventional network. And but I mean, now we can start doing all kinds of fun tests, like just treating the network really as a quantum states. For instance, remember that for each label, we have one quantum state. And then we want to see how entangled this quantum state is. And here's the plot, right? So we take the average of the 10 states because they all behave pretty much similarly. And then there are two data sets. One is the simpler one, that's the MNIST, the handwritten digits, and the other is the fashion MNIST, so as to classify these things, which is a slightly harder one. So they're both extremely accurate, as I said. And then the entanglement entropy trend is that you see that there's certainly a correlation, like the moment when the network is trained enough to perform well is also the moment when the network has obtained enough entanglement. And here the same thing for fashion MNIST, and we're looking at left-right entanglement just to be very concrete. And then we also tune the hyperparameter, like less channels, more channels, and different initialization and stuff. And then just keep running it. And then we see these different blobs representing different choice of hyperparameters. But I mean, there's still a clear correlation between accuracy or the negative of the cost function and the entanglement entropy. So that's the game we play. So it clearly suggests that the entanglement structure is a feature that the network has to learn in order to perform. And then you can think about, okay.
I have a question.
Yeah.
What is entangle with what here?
Right. So you can. This is our quantum states in the sort of tensor network like thing, right? And then you can design your let's say that the right hand side of your network represents, well, okay, let me say it in this way. I mean, a shorter answer is we have quantum states in the total Hilbert space, right? And then we compute the entanglement entropy in the usual way. Just trace over half of the Hilbert space. That's what we do.
Yeah,
and this half of
certain neural network is a certain state in the vectors in the Hilbert space, right?
Yeah.
So you have different neural networks operating in the same Hilbert space. That's what you're saying.
Yeah. So for instance, these correspond to these. Every dot is a different neural network.
And those neural networks correspond to different categories of objects or images, or say cats, dogs.
No. We average over the entanglement, the 10 entanglement entropies, because they tend to behave the same.
No,
so
the different vectors, the different states in the Hilbert space correspond to different neural networks, right?
You're talking about
the
different
states
neural networks.
Different neural networks.
Okay, so let me write it. So we have right?
Yeah.
You see? Yeah. So different network, you probably, I interpreted it as different theta, so different parameters. They're just different functions. But for each parameters, you have a y that's the number of labels. Maybe, for instance, in the digits example, from 0 to 9. So there are in two ways the state are different, but they all belong to the same Hilbert space.
What do the different states correspond to in terms of the neural networks? May I just interrupt, and because I think I can clarify the answer. I think the question is the following: what is the state? And the states are there are two states. You're mapping the input data to a set of states and the output data to a set of states. Is that right, Miranda?
No, the outputs. No. The outputs, which is the score function, right, is the overlap between the input states and the network state. Okay. That's the output are 10 numbers for each given input image. That's how classification works, right? You get 10 score functions at the end of the network. And then, for instance, if it's like 0.9 for the digit 9 and 0.1 for digit 1 and 0 other things as your score function, then the classification will say this is a picture of the digit 9.
Right. So, but your initial, the input to the network is a quantum state, right? You're mapping the image to a quantum state to begin with.
Yeah, that's the X state. Yeah.
Right. And so, what is the output state? What is the state on which you calculate the entanglement?
I'm computing the entanglement of this state, the network state.
The network state. I guess the difficulty is that it's not clear what you mean by the network state.
Yeah, so in short, the network state is the state such that this is true. And then the reason why I can always write the output number as an overlap is because of our special design of the network that can be represented as a tensor network without going too much in details. But if you put different elements of the slide together, you
yeah,
will see.
No, I understand. I got it. So what I was saying initially was you know, I understood what you were saying. You get an input state and an output state. You calculate the overlap as the score, and the entanglement entropy is the entropy between the different parts of the output state.
Yeah, no, of the network state. Yeah.
Or the output. Well, if I'll just call it the output state because it's less confusing to me in that. So, or you can call it the network state. You know, it's your paper. So.
Yeah, so anyways, I finished my talk. So the questions one can think about what to do with this is like, you want to, you know, you can look at the shorter range entanglement of the states to figure out what the state actually looks like, because, you know, since neural network has such an, bad reputation as a black box, so it gives you some tools to open the black box. And then, well, okay, this is some fun thing to do, but I mean, you can turn it into a generative model, not a classification model. So you can generate using quantum mechanical language a fake picture of digits or clothes. And it's interesting to ask what other types of data will give you different entanglement structure, or like what's the local Hamiltonian describing phi of y? Like what are we really minimizing in that language? Okay, and then how this is gonna shed light on architecture design and that kind of things. Okay, so thank you for your patience.
Thank you very much, Miranda, for the very nice talk.
Thank you.
So are there more questions?
Last part. So there's something I got confused about. So if I understand correctly, this last part you trained it on this NIST data set and maybe fashion NIST or something. And in that you found that, you know, when the network got trained, the entanglement entropy behaved in a certain way. But I thought the whole point about these deep neural networks was that, you know, they apply in all sorts of settings where you would not expect them to apply. I mean, as far as classifying the NIST data set goes, you know, it's not so surprising that you can train the network and it works. But, you know, maybe in playing chess or something, it's very surprising that something like this would work. So is there any reason to believe that this entanglement diagnostic would be useful in general? I mean, is there even a good way to define entanglement for, I don't know, for chess or for Go or something? And is there a reason it should, you know, when the network is trained that it should have learned entanglement? I mean,
right. So that's again a very good question, and I don't know the answer. But the key is obviously that you need to be able to make a neural network that emits an interpretation or description as a quantum state, and that already is non-trivial. Right, and then as I said, we picked CNN, which is just the sort of most canonical and, if you want, simple example of neural network to do the job. But for instance, I know people working on sort of quantum-inspired reinforcement learning and things like that. And once you have that, then you might be able to ask questions about more smarter algorithms, such as playing Go. And
all these current algorithms also, so I'm very ignorant, but I thought that what you're calling CNNs are what are the same as deep networks, and that they just have multiple layers with non-linearities. So it's you apply a matrix and then apply a threshold and one more matrix and a threshold. Is that correct? That's what a CNN.
Well, yeah. So deep networks have all kinds of architectures and they do different things. So CNN, for instance, is ideal for image processing because it explicitly it uses local, it uses locality. So you might wonder if you don't have a locality in your problem, then CNN is probably not, it's probably not a good, I mean, I should take the probably away. There's papers investigating using CNN to detect like topological faces is not so great.
So, but what's local here? I thought it's just a matrix followed by a threshold and a matrix followed by threshold. Where was locality? Network?
Right, but the locality is here. Here, for instance, the filter size is 3 by 3, right?
Oh, I see. Oh, it's not like an arbitrary matrix. You mean you apply like matrices to small elements only?
Yeah, CNN refers explicitly to this kind of architecture that's in contrast to this, fully connected.
Oh, I see. So is there some understanding of this quantum network for a fully connected network, or?
Well, yeah. So there's, for instance, where I'm starting to collaborate with some people on, for instance, the Boltzmann machine and kind of, yeah. So there's work on it certainly, and I can send you some papers.
Okay.
Very interested, but indeed, I mean, because I mean, it's not just like our work is purely just say academic. This paper, we're just having fun, like making an alternative that looks like CNN but admits a quantum mechanical description. We play with it. We measure. Well, we can measure entanglement entropy and see what happens. But I mean, there is a serious effort by industry people of like doing quantum machine learning, right? So there you really do quantum stuff.
Okay, thank you.
Okay, I have a question. Like when you plot the sort of trajectory of a quantum state, of the quantum state corresponding to a neural network, can you kind of glean the equations of motion for it? I mean, with respect to say some parameters, say time, with respect to iterations.
Like in what?
So with each iteration, it would.
Yeah, the training.
With each training iteration, it would go to a certain place, right? The vector, the Hilbert space vector, it would adopt some certain trajectory, right? With each iteration.
Yeah.
So if you treat the iteration steps as time, say. Can you devise some sort of Hamiltonian equation for?
Yeah. So that will give you, of course, if you can do that, of course, that's much more finer information than entanglement entropy. First comment is that this is again in very much the same flavor as the fourth bullet point, right? So are we minimizing some Hamiltonian, like?
Yeah.
Is this final? Yeah. So that's an interesting question. I think with enough human power and computer power, it's computable, at least approximately. Given if I give you our trained network, try to figure out what kind of Hamiltonian might do the job.
Okay.
So here, can you say why do you expect entanglement? Is it just because there are correlation between different parts of the image?
Yeah.
Or something like that?
Yeah, but actually, but then the question is how much entanglement? I mean, the fact that there has to be entanglement is unsurprising. And but then maybe what's interesting is how much entanglement do you need? And actually, there's also like a statistical estimation of mutual entropy, which is in some sense classical analog. So you can compare sort of that estimation of mutual entropy of left-right division of the MNIST data set with the quantum entanglement entropy. And they seem to be in the same order of magnitude, whatever that means. But yeah. I mean, yeah. again, in the network language, if the entanglement entropy is 0, that means the probability of something being 1 and the probability of a picture being 1 is the products of the two probability, which is, of course, would be quite a bad classifier, I imagine.
I see.
The Holy Grail, I suppose, would be a generalized kind of equation which applies across all sorts of neural networks, I guess.
I don't know what the Holy Grail should be. And we also don't know what is the space of all neural networks, right? It's pretty much like people come up with new architectures which do new things all the time. So it's still very much an experimental experience.
Yeah. No,
and the
what I was
trying
to get at is if you can sort of devise a sort of generic behavior of different neural networks, then when you apply it to some arbitrary neural network, some arbitrary problem, for some different problem, maybe you can apply those properties that you glean from those previous experiences and apply so that you don't have to train it all over again.
I mean, one comment, a few comments. So first comment is that this is one of the applications we have in mind, although we haven't really followed up on that, doing more work on that, but is that, okay, because we can approximate our architecture, not approximate is the wrong word. We can describe our architecture in terms of tensor network, and we know the theoretic upper bounds of the entanglement entropy that can be achieved by such a tensor network. And if your estimation of the required entanglement is too large of your problem, then you already know that don't apply this kind of architecture, it's not gonna work, right? So this kind of theoretical understanding. So that's a first comment. And then I forgot what the second comment is. I mean, just like in the tensor networks, right? If we know that MPS has certain, scaling, and if we know that if we have something that's beyond the area law, then maybe Mirror can do it, but the MPS is not going to do it theoretically. So you can already look at your system and know whether it's a good computational tool for your problem.
I just wanted to thank you for giving an awesome talk.
Oh, thank you very much. Thank you.
I was wondering, like, have you thought of applying this to, or thinking of this, like, in terms of holography also? Like, for example, it's a bit like learning the bulk state in terms of the boundary state or something like that.
Yeah. So those words certainly have entered my mind, but I mean, well, I think like, for instance, in those directions, there's some, I can maybe send you the reference later, like some references, some people, for instance, interpreting the neural ODE as a holography flow, and all that is very interesting and very appealing, but so far, I think I spend my time on just more practical aspects of things. Not so much, but I mean, yeah, those interpretations are certainly possible and potentially helpful. So for instance, in the project I'm doing, I'm also trying to, of course, this has been talked about before, that neural network is like an RG flow, but I'm doing some work trying to make that a bit more precise. Concrete. But there are certainly, yeah. But yeah, once you have the interpretation of RG flows, and then holography follows, right?
Thank you. Are there any more questions? Is it getting quite late, maybe?
It's okay. Okay. So yeah, thanks for an invitation, and hope to...
Yeah, thanks a lot for the great talk.
Thank you very much. Okay. So see you soon.
Bye.
Hopefully. Thank you. Bye. Take care.
Bye.
Bye. Bye.